A very good morning once again to all the participants. And I'm very happy and I thank your humble self to be here on time. As it is very much unseen in the perturbations of energy, so is the official work as well. So we are very unfortunate that Dr. Rajat Hegde sir has some unseen official business which had to be attended. But no worries, the FTP team has already worked through all the process, and we are very much happy uh, to have Dr. R. Vaira Vignesh with us for this session, and we are very much happy to have you, sir. So, Dr. Vaira Vignesh has a Bachelor of Engineering from Karbagam College of Engineering, Chennai, and he was the youngest to complete his PhD directly from after completing BE in Amruta Vishwavidyalpeetham. He was conferred PhD in 2019. To his credit, he has one patent, 10 book chapters, 35 plus conference publication, 45 plus research publication in peer-reviewed international journal. He was very much instrumental in setting up friction. Uh, he was very much instrumental in setting up friction stir welding lab and material processing lab in his research lab. Okay, he is now working as an assistant professor in Amruta Vishwa Vidyapeetham in Coimbatore campus. Uh, for his curriculum and academic achievements, he was awarded the Henry Ford Award, Best Academic Performer Award, Best Student Award from the Indian Society of Technical Education, New Delhi. Also, he also won Amruta Vishwa Vidyapeetham PhD scholarship consecutively 2 years. So we are very much happy to have you, sir. The session is over to you.
Thank you for the brief introduction, Chetan sir. So with this, I think we can move ahead with the session of today. Hope my voice is audible and it is clear.
It is clear, sir.
Yes.
It's clear. Okay, sir. We will proceed now.
Yes, thank you. So good morning, everyone. So I am Dr. R. Vaira Vignesh, serving as Assistant Professor in the Department of Mechanical Engineering, Amruta Vishwa Vidyapeetham, Coimbatore campus. In this pleasant day, we'll be discussing on synthesis and characterization of magnesium-based surface composites for biomedical applications in this ATAL-sponsored FDP on novel nanostructured magnesium-based alloy for industrial and biomedical applications that is organized by Jawaharlal Nehru National College of Engineering, Shimoga. So Chetan sir has given a brief introduction about myself, so I'm just skipping over this slide. And before I move into the topic of discussion, I would like to introduce the lab that I'm associated with. So I'm part of friction stir welding lab at Amruta. So in this lab, we work on friction stir processing of lightweight materials to develop ultra fine grained materials, surface modified materials, and surface composited materials too. We also work on friction stir welding, spot welding, and rotary friction welding uh, to develop sound solid state joint in similar and dissimilar materials. And right now we are ventured into modified friction stir clinching process. So that is done to eliminate the inherent keyhole defects that happens in FSP, FSW, or FSSW process. And we also work on friction surfacing of metallic materials to improve their corrosion as well as tribological performance. So in computational domain, we work on hybrid statistical modeling, computational optimization, and simulation of thermal phenomenon in friction assisted processing and welding. And speaking about the next lab that I am associated with, materials processing lab. So this lab was set up by the funds from ISRO, Department of Science and Technology, and Amruta Vishwa Vidyapeetham. We have the following facilities over here. And we work on brake pad specifically, and Dr. M. Govind sir is one of the expert who is working on vacuum brazing of materials. And these are a few glances of the technologies that are developed at Amruta Vishwa Vidyapeetham. So we have developed technology for ceramic to metal seals by semi-solid processing. Also, we have developed ceramic coated bearing components. We have developed honeycomb structures, and right now we are also exploring the possibilities of joining ceramics to metals, and we are exploring a lot of things in that. And coming towards sustainable engineering solution that is developed at Amrita by our research team. So we have developed a composite paver block, a technology for recycling waste polymer and fly ash, and that has been applied for patent very recently. So environmental conservation policies mandate the replacement or recycling of polymer-based domestic products or components. So generally, this fly ash is mass produced in this thermal power plants. So and they are just dumped in dump sites, and that aggravates environmental pollution, including groundwater resources too. So devising effective waste management strategies or developing technologies for recycling waste is the need of the hour. So our team have worked tirelessly to develop this technology for the fabrication of composite paver block using shredded and pulverized polymer waste as well as fly ash. And that has been recently applied for a patent with the intellectual property of India. And with this, I'm just going ahead with the outline of today's presentation. So I'll just briefly give an introduction about conventional implants. Then we'll discuss on the need for biodegradable implants and the materials that is conventionally used for biodegradable implant materials. Then we will discuss the limitations with respect to materials as well as the processing methodologies involved in the fabrication of biodegradable implants. Subsequently, I will introduce to the concept of friction stir processing, and I'll discuss our research work based on friction stir processing of magnesium alloy AZ91 for biodegradable implants, as well as we discuss friction stir processing of magnesium alloy AZ91 with nanophase silica reinforcements. Then we'll just have an overview about the entire thing, that is the summary of our presentation. And if time permits, then we'll see the creep performance of magnesium, how it can be augmented using friction stir processing method. So generally, implants are any materials that are engineered to interact with the biological systems. So implants are utilized for hard tissue bone fractures predominantly, and they substitute or support the functionalities of the human cortical bone. And generally, people use polymeric, ceramic, or metallic based materials for implants. The problem with polymeric materials is that most of the polymers lack biocompatibility. And coming towards ceramics, the machinability is obviously limited. So generally people use metallic materials such as stainless steel, chromium, tungsten, titanium, or cobalt chromium based alloys, preferably for implant applications. So here is a detail about the properties of bone as well as the conventionally used implant materials presented as a table. So here we can see the density of bone is in the range of 1.8 to 2.1 gram per cc, and the conventional metallic materials, that is stainless steel, titanium alloys, cobalt chromium or tungsten, have density very much higher than that of the human bones. Added to that, the compressive yield strength, the Young's modulus values of these conventional materials are so much higher than that of the human bones. So this undesirably high strength and high Young's modulus is not so much recommended for metallic implant materials. Why? Because if we use them in the human body, there is high tendency for the implant material to absorb the stresses that are transmitted to the specific area of the body, and that in turn will induce body mechanism to reabsorb developing bone material, and that in turn deteriorates the bone density completely. So all these process leads to loosening of the implant, and in turn leads to bone refracturing. So this entire sequence is termed as stress shielding effect. So the stress shielding effect is not completely eliminatable in case of conventional metallic materials. Added to that, these materials are non-biodegradable. That means we have to perform a secondary revision surgery once the bone heals completely. So we are what to say, decreasing the patient's ability to heal within a very short period of time. Added to that, the corrosion as well as the wear debris produced by these metallic materials is not biocompatible too. So that will increase the toxic ion concentration within the vicinity of inflammation, and that leads to inflammatory osteolysis. So these things create the necessity for development of new metallic materials. And not only that, coming towards biodegradable implants. So people are switching over from conventional implants to biodegradable implants very shortly, and that is practically applicable only if the implants are implants are made into human body for a short duration. So here's a typical graph that shows how regenerating bone gains strength over a period of time, right from 0% to 100%. 0% indicates the fracture root time, and 100% indicates the full growth time period. So when we use a conventional implant material, the strength of that particular metallic material will not degrade over a time. So its strength remains constant over the entire duration of bone healing period. So that is what it is shown in gray color trend line. So people started to explore the concept of biodegradable implants. So these implants have the inherent ability to corrode within the human physiological environment. But the thing is, currently used biodegradable implants completely goes into the body and they are excreted as ions before the bone heals completely. So this completely restricts the functionality of the bioimplant material. So we have to develop a biodegradable implant material that has gradual loss in material as well as mechanical strength during the degradation process that would be balanced by the increasing strength and ductility of the newly forming bone. Only if that is done, then we can achieve the concept of a good biodegradable implant material. Added to that, this biodegradable implant should support tissue regeneration and healing by dissolution, resorption, and formation of corrosion products that enhance osteoconductivity. So these are the primary requirements that is put forth by the what is it biodegradable implants towards the materials for effective functionality. And these are some of the key advantages of using magnesium as a candidate bioimplant material for uh, biodegradable implant application. So here the density of humans as well as the magnesium alloys are in the within the specified limits. That is, the density of human bone is around 1.8 to 2 gram per cc, and magnesium alloys have density between 1.7 and 2.1 gram per cc. And the compressive strength of human cortical bone and magnesium alloys are more or less similar, and they are in the range of 130 to 180 megapascals. And the Young's modulus of human bones is very much similar to magnesium alloys. So, which means that there will be limited stress shielding effect than any other metallic materials if we use magnesium alloys. And added to that, magnesium has the inherent ability to corrode in the physiological environment, which is rich in chloride ions. So these things make magnesium as one of the candidate material for biodegradable implant applications. Not only this, the magnesium ion is one of the cofactor of more than 325 enzymatic reactions that are required for proper functioning of the internal organs too. So when magnesium is corroded in the due course of inflammation period, ions will be liberated, and that in turn will be utilized by the human body itself for creating hormones or whatever enzymatic reactions it can be. And added to that, the serum magnesium level within the human body is maintained by the dynamic absorption and excretion equilibrium of magnesium ions by the kidneys. So when there is an increase or peak in magnesium ion concentration within the bloodstream, our body internal organs will take care of. They will be eliminated through excreta or through urinary tract. Added to that, World Health Organization recommends a daily intake of 280 to 300 milligram of magnesium for adults as well as 250 milligram for children. So, which means that even if magnesium goes into body, that is not going to harm our body completely. So that makes magnesium alloy as the candidate material for biodegradable implant applications. However, there are certain limitations with magnesium too. So, as we all know, whenever a material is subjected to a load, it deforms by slip or by twin. So, slip system is a set of symmetrical identical planes and corresponding slip direction in which dislocation may occur, and that leads to deformation of the material. So, this case of magnesium, it is hexagonally close packed structure. So, it has only three slip systems that includes basal plane, prismatic plane, as well as the pyramidal plane. So, generally, polycrystalline materials require at least 5 independent slip systems for deforming without any failure at the grain boundaries. But in case of magnesium, since it is having a HCP crystal lattice, it deforms by twinning. So deformation is affected by primary prismatic and secondary pyramidal slip systems. Okay, so that has to be accounted in when we ought to think about the manufacturing probabilities of magnesium. And coming towards the machinability characteristics. So activation of non-basal system avoids twinning. So people may argue with us stating that magnesium, if it is subjected to high temperature processing, that may lead to some sort of improvised machining or machinability index. But that is not so. Why? Because activity or critically resolved shear stress of non-basal systems is dependent on temperature as well as solute concentration in the matrix. The CRSS for the secondary pyramidal slip systems has a positive temperature dependence, as well as the CRSS for primary prismatic slip systems have a negative temperature dependence. So which means that we can never ever expect magnesium to deform so much good even if it is processed at high temperature. Okay, and the typical case, we can see any sort of rolling process or machining process or whatever it can be. So it deforms very in a challenging way. So these all parameters have to be considered when we take magnesium into account for biodegradable implants. Why? Because we'll be machining very complex structures for implant applications. And not only that, there are few more challenges that is posed by magnesium for being an implant material. As we have discussed, because of HCP structure, it has low workability. And also, this magnesium is a highly active metal, which means it has high tendency to corrode, as well as uh, because of its low density, it has high tendency to be worn off easily. Added to that, this corrodes very rapidly at the pH range of 7.2 to 7.4. So typically human beings have pH between 7.22 and 7.4. And in that case, magnesium corrodes at very high corrosion rate of around 4 to 8 mm per year. So in case if we implant magnesium very directly into our body, that will result in accumulation of hydrogen gases in the tissues, which is a lethal phenomenon. So we have to do a process, or we have to fabricate a composite out of this magnesium so that we can engineer the corrosion properties of magnesium so that we can bring down the corrosion rate to recommended corrosion rate of less than 0.5 mm per year. So this is the primary thing that we have to take care of when we consider biodegradable implants. The primary point is the corrosion rate should be well below 0.5 mm per year at any time period of implantation. And coming towards the base material selection, so I'll be going towards case study based approach with respect to this webinar, and coming towards the materials that is employed in biodegradable implants. People have been utilizing this AZ31 alloy, AZ91 alloy, LAE 442, AM60, and rare based magnesium alloys such as WE432. But what we have selected is AZ91 alloy, which is a magnesium aluminum alloy system. Why? Because that has shown good compatibility as well as corrosion resistance in vivo experiments that we have done in the base material. So we have chosen AZ91 as our base material, and we have taken wrought alloy of thickness 4 mm into this study. And as we all know, the composition of AZ91 is shown over here. So the composition of AZ91 is as follows. So aluminum, it will be around 8 to 10%. In the material that we have taken has aluminum of around 8.72%, and zinc is the secondary alloying element that is added to magnesium in this case of AZ91 alloy. So that has a concentration of 0.51% in this case. So which means that we are adhering to the materialistic standards. So we have taken this material and then we have proceeded. And even before proceeding, we should understand the intermetallic phases that are present in the alloy system particularly. So as we all know, the solubility of aluminum in magnesium is very much limited. Only 11.5% of aluminum dissolves at the eutectic temperature. And beyond that solubility limit, magnesium 17Al12, a brittle intermetallic phase, precipitates out. and that is thermally unstable too. So we can engineer that intermetallic phase through either hot working process or any severe plastic deformation processing techniques. So why there is a high tendency for corrosion in AZ91 alloy too? So that is what it is explained over here. So as described, the corrosion potential of alpha magnesium, that is the primary phase of AZ91 alloy, is minus 1.81 volt against standard calomel electrode in Hang solution. Hang solution is nothing but a solution that mimics the human body environment. Similarly, the beta phase, which is the secondary phase that is present in AZ91 alloy, has corrosion potential of minus 1.08 volt against standard calomel electrode in Hang solution. So because of this potential difference, we end up with galvanic coupling effect and also intergranular corrosion effects in this AZ91 alloy, and that leads to very high corrosion rate in AZ91 too. Okay, and the presence of active phases results in high tendency for loss of electrons than that of the passive phase. So which means the activity is also required for a certain corrosion product formation. So that we will see in detail in the upcoming slides. Why the activity is also required in case of biodegradable implant applications. So we have done this microstructure analysis and XRD phase analysis. So microstructure analysis shows that we have alpha phase as well as beta phase, and in the base material, the beta phase is continuously networked within the matrix, and we have analyzed the same using scanning electron microscopy too. We have received the same results. That is, we have a continuous network of beta phase in the AZ91 alloy, and that is the primary factor that contributes to a very high corrosion rate of around 4 to 8 mm per year in conventional immersion techniques. XRD analysis also confirmed the presence of alpha as well as beta phases in this AZ91 alloy. The micro hardness of this AZ91 alloy in the as fabricated condition is around 57.9 HV against a load of 9.8 newtons. So to assess the basic tendency of this AZ920 alloy, we have done this immersion corrosion test. So in order to assess the change in pH, also we have done experiments. So these experiments are carried out with respect to the standard ISO 10993 part 15, and here we have particularly utilized Dalbeco's phosphate buffered solution, which is a simulated body fluid solution, and we have maintained all our immersion corrosion test at around 37 degrees Celsius with an accuracy of 0.1 degrees Celsius using a thermostatic water bath, and we maintain it at that temperature so that we can mimic the human physiological environment, and we had a close control over the pH throughout the entire testing duration. So the test was conducted for a period of 7 days. We have closely monitored the pH with a sensitivity of plus or minus 0.1. And after that, we have analyzed the corrosion surface morphology, corrosion product morphology after 24 hours, 48 hours, after end of 1 day, 2nd day, 3rd day, 4th day, 5th day, and 7th day. And right after analyzing this, we come to a conclusion that the concentration of hydrogen ions actually decreases with an increase in immersion period. So that attests that there is evolution of hydrogen gas when magnesium is immersed within the human body solutions. So added to that, the corrosion rate of this magnesium alloy after 24 hours of immersion is 4.37 mm per year as described in this figure. So the corrosion rate is some sort of very much high with respect to base materials. And with respect to increase in time, corrosion rate decreased and stabilized at an average corrosion rate of 1.05 mm per year. And that also happened after 144 hours of immersion. So which is a very long inclination period when it is considered. So we can see that the corrosion rate of magnesium alloy in the as fabricated condition is very much higher than the recommended corrosion rate of 0.5 mm per year. So we have to do some process so that we can engineer the corrosion rate to well below 0.5 mm per year. So that is point one that we have to understand. And next come towards the analysis of corroded specimens. So here is the image that shows the corrosion surface morphology after first day, third day, fifth day, and seventh day. So that is what it is shown towards the right, A, B, C, D. So here we can see that the cracked surface had widened with immersion time. With increase in days of immersion, the crack started to widen. However, the morphology of the corrosion products changed with respect to the first day and with respect to the last day. In the first day, we can see flower-like clusters that has been bloomed over the entire surface of the specimen. However, in the subsequent days, they are completely removed off. They may be formed as a uniform corrosion layer over the specimen, and there is typical branch-like structure formation in corrosion products too. So we thought of analyzing the corrosion products in detail. So we have done EDS and XRD analysis. So the peaks indicated, the EDS analysis peaks indicated the presence of magnesium, sodium, calcium, phosphorus, chlorine, as well as oxygen in specimen 1, that is after 24 hours of immersion. So the calcium to phosphorus ratio should be taken into account. Why? Because we are immersing this thing into human body solution, which is rich in calcium, phosphorus, as well as chloride ions. So when we take this calcium to phosphorus ratio, it is around 2.15 in case of specimen that is immersed after 24 hours of immersion in the corrosion products. And subsequently, the corrosion product had calcium to phosphorus ratio of around 1.65 after 7 days. So it means that there is typical change in the chemical structure as well as the chemical composition of the corrosion product that has been formed right from day 1 to day 7. So when we do this XRD analysis as well as elemental mapping analysis, we can come to a conclusion how this corrosion product is consisting of or what it could be. So we have taken this elemental mapping. So here we can see that the elemental maps of calcium, phosphorus, oxygen, and whatnot, calcium, phosphorus, and oxygen, they are in line with each other, which means the corrosion product consists of all these elements in their structure. So when we take this calcium to phosphorus ratio as well as the overlapped map of these individual elements from this EDS analysis, we can confirm that there is formation of hydroxyapatite crystals within the on the surface of the corroded specimens with respect to increase in immersion time. So this calcium reduction favors the formation of hydroxyapatite crystals to a greater extent. Since magnesium is also into the picture, it will form calcium magnesium phosphate crystals also. So that is also reported in the literature. This calcium magnesium phosphate or this hydroxyapatite crystals are having very much relationship with our bones. Why? Because bones are made out of this hydroxyapatite crystals only. So we can confirm that if these are formed on the surface of the corroded specimens, the exact scenario of bone is being replicated over the specimen also, which means the living cells will just come over to the implant sites. They just adhere to them without any sort of hesitancy. So these just give us an intuition that this material, if it is employed in biodegradable implant, if it is used as a biodegradable implant material, it will have a good biocompatibility too. However, we have to understand the corrosion rate is still higher, way higher than 4 to 8 mm per year. So we have to bring that down. Biocompatibility is fine, but we have to engineer the corrosion rate so that we can have a controlled degradation kinetics with respect to magnesium alloy in the human body environment. So that has to be taken care of. So we have wide opportunities for processing it. So XRD peaks also confirmed. I hope I have said about it. So XRD analysis confirmed that the peaks between 20 to 35 degrees indicated the presence of calcium magnesium phosphate as well as calcium hydroxyapatite crystals. Okay, so not only EDS map, not only this calcium to phosphorus ratio, also this XRD analysis confirmed the formation of calcium, magnesium phosphate, and hydroxyapatite crystals, which is so much crucial for increasing the biocompatibility of the materials when it is implanted within the human body. So with this, we'll see opportunities for processing magnesium alloy. And people have tried out various heat treatment methods for improvising the properties of AZ91 alloy. So that could be mechanical, corrosion, or typological, or whatever it can be. Then people started to explore the opportunity of alloying with additional elements such as calcium, cerium, neodymium, bismuth, cerium, strontium, yttrium, etc. So, however, these rare earth elements have some sort of decreased biocompatibility with respect to human body. So that has to be taken care of very, very cautiously. So alloying elements is going to be something deleterious, or it is going to be time consuming. So people started to explore addition of reinforcements such as titanium carbide, titanium boride, magnesium silicate, etc., etc. So even that also has given some promising results. Then people tried out deformation processing techniques like equal channel angular pressing, extrusion process, accumulative backed extrusion process, or differential speed rolling process, Kobo processing methods, etc., for improvising the characteristics of this AZ91 alloy. And people also followed plasma spray process, electron beam process, surface welding process, or surface coating methodology such as electroless deposition of nickel, electro deposition of compounds, magnetron sputtering, etc. And people tried this unconventional processing methodologies such as spray forming methods, laser surface melting methods, and cryogenic treatment methods too. So these are many, there are many opportunities for fabricating magnesium alloy. However, there are certain limitations of these processes. First is the complex surface preparation as well as process methodologies. So these processes have to be ensured. These processes have to be done under very strict conditions. So the surface preparation is going to be very complex in this case. And the process dependency on properties of magnesium alloys also limits their process that can be applied for magnesium. For example, since it has HCP structure, we cannot cold work it. And coming towards the liquid state processing of magnesium alloys, it is going to be very, very challenging. Why? Because it leads to rapid surface oxidation, undesirable intermetallic formation, and subcutaneous grain growth. And induction of residual stresses is also another phenomenon that is generally observed. And distortion, shrinkage, all comes into the picture too. And we will be observing defects such as porosity, spatter, and voids if magnesium is subjected to a liquid state processing and if the environment is not taken care of very properly. So these mandate the requirement of shielding or vacuum environment for processing magnesium alloys, and that is going to be a high energy requirement process. So these necessitate development of new processing methodology or utilize some methodology that has overcome all these limitations. So one such processing way is solid state processing. Magnesium is so much suitable for solid state processing, and particularly we'll be discussing on friction stir processing, which is one of the solid state processing techniques. So in this case of friction stir processing, we use FSW tool. Okay, so that has a specific morphology. So that is what it is shown over here. So this FSP tool will be put into the workpiece. It will be traversed under the action of axial load. And because of this traverse as well as rotation, and because of frictional heat generation, there will be lot of microstructural changes that happens within this material when it is subjected to friction stir processing. So this process is particularly advantageous. Why? Because we will go a maximum of temperatures which is less than 0.5 times the melting temperature of the material. So which means we do not allow any sort of external reactivity of magnesium, external agent reactivity with magnesium that is being processed. And added to that, these processes advantageous. Why? Because there is meager induction of residual stresses and there is no deliberate inclusion of new phase materials into the matrix. This FSP is also advantageous. Why? Because this helps in disintegration as well as partial dissolution of secondary phases which is present within the matrix. Added to that, this process aids in grain refinement too. So we'll see how that happens in detail in the next slide. So most of the properties of this friction stir processed materials depends on the extent of recovery and recrystallization phenomenon, as well as the material flow characteristics that happens in the material. So we'll see what this recovery and recrystallization phenomenon may be very shortly, so that we can proceed with the important results in detail. So generally, we classify the working process as hot working process and cold working process. And this hot working process, mostly they will have dynamic recovery and dynamic recrystallization. And cold working process will have static recovery and static recrystallization. In case of friction stir processing, it is very, very unique. Why? Because it introduces both heat and strain into the matrix simultaneously. So obviously, when a tool is plunged into the workpiece and it is being traversed, the zone which is exactly beneath the tool is denoted as zone B, and that will undergo dynamic recovery, dynamic recrystallization, and subsequently grain growth phenomenon. Whereas the zones in the workpiece which is ahead and behind the FSP tool will undergo static recovery, static recrystallization, and grain growth phenomenon. So this is so much advantageous with respect to processing. Why? Because we end up with static as well as dynamic recovery and recrystallization that will result in refinement of grains to a greater extent, breakdown of particles to breakdown of secondary phase particles to a greater extent, and that all cumulatively lead to improvised mechanical as well as corrosion properties too. So that has to be understood. So how this happens? So we all know static recovery happens only if the deformed material is subjected to a high temperature condition. So only if it is subjected to a high temperature process, that is the deformed material being subjected to a high temperature, then the structures will rearrange into stable arrays, and that will form walls of dislocation that leads to formation of subgrains. Added to that, since this AZ91 alloy has second phase particles, they influence the low angle grain boundaries too, and they ensure that the misorientation between two grains is less than 15 degrees, and that all happens because of the Zener drag effect. And the presence of second phase particles reduces the subgrain growth and promotes dislocation preservation too. And these second phase particles impede the dislocation motion with opposing shear stress that is significantly possible only if they are in the size of few nanometers. So this FSP process is capable of producing nano level of reinforced second phase particles within the matrix, and that could be visibly seen using transmission electron microscopy. So that also we'll see in detail. So added to that, these dislocations in the deformed microstructure reorganizes to form strain-free grains. So that is what we call a static recrystallization. And in this case of static recrystallization, we end up with strain-free grains from these strained grains. Okay, so this also is advantageous. Why? Because we end up with reduced residual stresses within the matrix too. And added to that, growth of recrystallization grains is interface controlled. So coming towards dynamic recovery and dynamic recrystallization process, so rearrangement and annihilation of dislocation structures during the processing itself or during the deformation process itself is called as a dynamic recovery. And if you continuously apply this recovery phenomenon or recrystallization phenomenon, and that leads to dynamic recrystallization, and continued application of strain introduces new dislocations into this decrystallized grains which is already present, and that leads to formation of subgrains and inhibits its further growth. This additional straining results in new nucleation sites for recrystallization, and that leads to series of recrystallizations within the matrix. So that is what we call discontinuous dynamic recrystallization. So this also particularly happens in case of friction stir processing of magnesium alloys, and that is also advantageous. Why? Because we end up with refined microstructure with fragmented beta phase. So that is the major point that we have to understand. So these are the science behind fragmentation as well as formation of strain-free grains. in friction stir processed magnesium alloy. So we'll just jump into the results part in detail as of now. So initially we thought of doing some uh, ex- uh, exploratory analysis. Okay, so we have started our experiments with tool rotation speed between 600 rpm. I mean, we have started with 600 rpm, 20 per minute, and in that case, we ended up with some sort of defects in the specimen too. So that is what it is shown over here. In case of specimen FSP02, that was processed at an RPM of 900, and it was processed at a tool traverse speed of 20 per minute. In that case, we have observed root flow defect, and that is because of high tool rotation speed as well as low tool traverse speed. And that combination resulted in the formation of onion ring morphology as shown in the figure over here. And because of this combination, that is high tool rotation as well as low tool traverse, it created a turbulence and obstructed the flow of the particle, and that resulted in the formation of a root flow defect in the material. And coming towards specimen FSP03, that specimen had scalloped surface, and that is a distinct feature on the borders of a semicircular pattern that is shown in this figure B over here. So that is because of low tool rotation speed of around 600 rpm and high tool traverse speed of 60 per minute. And because of such combination, there is poor material flow and material transfer in the material, and that is why we ended up with scalloped surface. In case of FSP06, that is processed at 962 rpm and 40 per minute, we ended up with narrow groove, and that is because of high tool rotation speed as well as medium tool traverse speed. And because of such combination, there was a turbulent flow of material as well as non-filling in the processing direction, and that resulted in the formation of a narrow groove in the material. So just by observing the surface, we have eliminated the specimens FSP02, 03, 06 for the further analysis, and all other specimens are taken into account for microstructural analysis. So here is the microstructure of the base material as well as the typical microstructure of the friction stir processed specimen. So we have done initially macrostructure analysis using non-contact optical profilometer that has a resolution of 0.1 nanometer. So from here, the macrostructure analysis reveals that the main forms of the surface defects that happens in the material are onion ring patches, feed marks, scratch marks, tearing surface, and chip layers too. And feed marks, as we all know, it is a discordant that forms when there is a discordant combination of tool rotation speed and tool traverse speed, and they are relatively parallel and equidistant from each other. And the feed marks distance between them is influenced by the tool traverse speed. If the tool traverse speed is very high, then we'll end up with very large distance between any two feed marks. That means that it is a good surface finish. In case if it is feed marks are relatively close to each other, it means that there are many sort of surface deflections that have happened in the course of friction stir processing. So that we have to understood. So feed marks were observed in the specimens FSP01, 2, 4, 6, and 9. And that is all because of high tool traverse speed. And in case of low tool traverse speed material, there were feeble trace of feed marks in the specimen FSP01. High TTS resulted in significantly clear and deep feed mark in FSP03 and not in FSP01. It is in FSP01 typically. FSP01, it is low TTS, and there we have observed only low or feeble tracks of feed marks. And added to that, we have observed some highly plastically deformed surfaces, that is protuberances in specimen FSP05, and that has resulted in highly deformed surface. And extremities in tool traverse speed as well as tool rotation speed resulted in the formation of microchips as well as dimples in the specimen FSP07 and FSP08. So this high TRS promotes fusion of microchips and debris. So we have observed some adhering particles in specimen FSP06. So among all these specimens, specimen FSP04 and FSP09 had minimum surface defects. And after this macrostructure analysis, we have done this microstructure analysis. So it is what is shown over here. So here we can see in the base material, there is a heterogeneous microstructure, which means there is primary alpha magnesium dendrites and coarse continuous network of beta phase particles within the matrix. Whereas in case of friction stir processed material, we can see a refined microstructure in which we have few particles of beta phase that is embedded in the alpha magnesium matrix. So here we have a dispersed beta phase within the matrix. Added to that, the networked fashion of this beta phase is completely disappeared after friction stir processing. And we have done this XRD analysis too. So that also has confirmed the presence of alpha phase and beta phase, and there is no formation of any other phases other than the particular phases that is mentioned, that is alpha magnesium as well as beta magnesium 17 Al12 in case of friction stir processed AZ91 alloy. And among all the specimens, specimen FSP07 had the highest micro hardness, and FSP09 had 4% lesser micro hardness than FSP07. However, the specimen FSP09 had better surface finish than the specimen FSP07. So that is evident from the surface roughness values that is shown over here. So among the micro hardness, so FSP02 had least micro hardness of 56.33 HV, and that is all because of the root float effect that we have said already. And FSP07 had the hardness of 80.87 HV, so that is 40% higher than the base material. Next comes the immersion corrosion test. So the immersion corrosion test was performed as per the discussions in AZ91 alloy. So in the base material category, we have discussed some immersion corrosion test. So the same procedure is followed for this friction stir processed material too. So here we have done immersion corrosion test for most of, for all the specimens. So here we can come to a conclusion that after 36 hours of immersion, the base material had a corrosion rate of 7.6 mm per year, and FSP07 had the least corrosion rate of 1.165 mm per year. So that is 85% lesser than the base material. And among the friction stir processed specimen, FSP05 had the highest corrosion rate of 4.533 mm per year. And after 72 hours of immersion, the base material had a corrosion rate of 4.51 mm per year. Though there is a significant reduction in base material's corrosion rate, the corrosion rate is still significantly higher in case of base material. In case of friction stir processed specimen, FSP09, after 72 hours of immersion, their corrosion rate reduced to 1.023 mm per year. Though the corrosion rate is lesser, still it is way much higher for biocompatible applications. And coming towards the specimen FSP05 that had highest corrosion rate in 36 hours of immersion, that had a corrosion rate of 2.877 mm per year after 72 hours of immersion. So just by analyzing this immersion corrosion test results, we can see that the specimen FSP07 and FSP09 is exhibiting the at least near to level corrosion rate even after 36 hours or 72 hours of immersion precisely. So we can see there is a decreasing trend with respect to corrosion rate with an increase in immersion time. So that is all contributed to the formation of corrosion products over the specimen surface. So here also we have done the same analysis, that is elemental composition analysis was done. We have done this XRD analysis, elemental mapping analysis was done. So based on the analysis, we can see that here also in friction stir process specimens, we have calcium hydroxyapatite, calcium magnesium phosphate, as well as reduction in calcium to phosphorus ratio right from 2.05 to 1.45. So these things confirm that even in friction stir process specimens, we get this calcium hydroxyapatite formation. So that makes friction stir processed magnesium alloy as also a biocompatible material. However, we have to keep it in mind, the corrosion rate is not so much better in this case also. Okay, so previous studies have suggested that the formation of hydroxyapatite supports the bone growth and implant bone integration. So here in case of friction stir processed magnesium, we have this evidence to show the formation of hydroxyapatite. So this is a biocompatible material. However, we need to further refine the corrosion rate of this particular alloy. So how do we do it? So that we will discuss in detail in the upcoming slides. So even before going that, we needed to confirm whether it is biocompatible or not. So just by saying some words, we can never ever say whether cells will have any toxicity effect with respect to friction stir processed magnesium alloys. So we have done this biocompatibility analysis. So where we have taken or extracted the friction stir processed specimen in the specified medium. Then we have conducted cell proliferation studies. Okay, and that was done with the standard 10993 part 3, and we have seen that the cell proliferation is so much good in case of base material as well as friction stir processed specimen. More or less, the proliferation has not decreased in case of friction stir processed specimen. So, which attest that friction stir processed specimen could also be one of the effective biocompatible materials. Still, further corrosion resistance has to be improved, but even if compatibility is somewhat better. And coming towards the outcomes of this friction stir processing, I'll just discuss briefly. Then we'll see the methodology to further reduce the corrosion rate of AZ920 alloy in detail. So here we had taken wrought AZ920 alloy, and then we have made a homogeneous microstructure through friction stir processing technique, and we have completely eliminated the networked fashion of beta phase in this AZ920 alloy. And among the specimens that is friction stir processed, we can see that highest corrosion resistance is observed in specimen FSP09, which is processed at 750 rpm and 40 mm per minute. And the grain refinement submicron beta phase has improved the micro hardness corrosion resistance of friction stir processed material. So hope this is understood. So, however, the research is not complete since the corrosion rate is still way much higher for biodegradable implant applications. So we thought of making a surface composite out of this magnesium alloy AZ91D so that we can end up with an engineered corrosion rate. So for that, we have taken magnesium alloy. We have tried with n number of reinforcements. Among that, one of the reinforcement is nanophase silica. Why? Because this silica phase has good compatibility with human body environment too. So that is why we have taken nanophase silica. We have even tried with reinforcing micron phase hydroxyapatite, nanophase hydroxyapatite in our AZ920 alloy. Even that results also so much promising. However, I'll be limiting my case study towards this surface composite of AZ920 nanophase silica. Okay, so this is the brief overview about that process. So we had good grain refinement, and there was a good dispersion of nanophase silica within the matrix. Corrosion resistance was so much higher. There is formation of biocompatible corrosion products even after reinforcement of nanophase silica within the matrix of AZ920. So we have done friction stir processing, or we have utilized this friction stir processing for fabricating the surface composite. The methodology is just shown over here. So here we have taken a workpiece of dimension 150 by 50 by 4 mm, and then we have made a rectangular groove of 150 by 100 by 1 mm by 1 mm. So 50 mm, 25 mm 25 mm. We have left for fixtures. And then the groove was filled with nanophase silica, and it is compacted. And then we have done a sealing pass. So the sealing pass is done with an FSP tool that is devoid of pin in the shoulder. So that inhibits the scattering of reinforcement particles. And then we have plunged the tool, FSP tool, into the workpiece. A dwell time of 30 seconds was adopted, and then FSP trials was performed. We have done consecutive passes, that is pass 1, pass 2, with a dwell time of 60 minutes. Okay, for instance, if pass 1 is done at 10, then the pass 2 would be done at 11. So that's it. So that is the dwell time in case of consecutive passes. And the dwell time for tool plungement to the FSP is just 30 seconds. And coming towards the defect analysis, so we have done a few trials in this case of surface composite fabrication too. So here is the typical images of CM01, CM02. So that is shown in figure A and figure B respectively. So that we can see full defects as well as wormholes in the specimen. In case of specimen CM03, we had flash, that is protruding structures, fill defect, as well as wormholes when it is observed along the transverse section. In case of specimen 0, CM04, that is processed at 1 minute. Yeah, that was processed at 900 RPM and 40 mm per minute. We have observed flash and wormhole. Whereas in case of specimen CM05 and 06, we have observed wormhole and fill defect respectively. So in case of specimen CM07, that is friction stir processed at 900 RPM, 20 mm per minute, and subsequent 2 passes, there is no defect at all. So we have taken that as our optimum parameter. We have fabricated our surface composite using this parametric level, and then we have subjected all the specimens to analysis. So we'll see that in detail right now. So initially we'll see the microstructure of surface composite. So the CM07 in the stir zone, thermomechanically affected zone, and the base material zone is just shown over here. So here we can observe the thermomechanically affected zone that had EQ acts to fine grains, and in particular in TMAZ they are oriented along a particular direction. So that is what it is observed over here. So I'm just pointing that with the laser pointer here. We can see there is flow of material particularly in this direction. So that is the orientation of grains with respect to the stir zone. And in this stir zone, the image is shown in B. So there we can see very fine grains that happen because of recrystallization phenomena. And added to that, these refinement is attributed to pinning effect of nanophase silica particles. Why? Because these nanophase silica particles nucleate the magnesium grains during recrystallization process. Added to that, these nanophase particles restrict the growth of recrystallized magnesium grains too. So these cumulative factors enabled formation of refined grain structure with fragmented beta phase within the matrix of the surface composite, particularly in the stir zone. So we have seen the microstructure using this high resolution transmission electron microscopy to confirm the formation of nanophase or submicron phase beta phase, as well as to analyze the presence of nanophase silica particles too. So here in the high resolution transmission electron microscopy image, we can see the grain boundary. We can see the partial dislocations that had formed as a sequence, and that resulted in the formation of subgrain structures within the matrix. So all is visible in this transmission electron microscopy image. So here we can see the homogeneous dispersion of nanophase silica as well as the presence of submicron beta phase particles within the matrix. We have done this SAED analysis, that is selected area electron diffraction analysis, to confirm if there is a that particular particle which is shown as black colored one over here is a submicron beta phase or not. So the SAED pattern confirmed that the black colored dot, which is in submicron size, it is a submicron beta phase particle. And coming towards the next analysis, that is EDS as well as XRD. So we have done that to confirm again the homogeneous dispersion of nanophase particles within the matrix, as well as the presence of alpha phase, beta phase, as well as the reinforcement is confirmed through XRD analysis also. So here we can see that the peak, which is between this 10 and 30 degree, correspond to this nanophase silica particle. So that is evident from XRD analysis too. So next we have done this micro hardness analysis. So this was done using Vickers micro hardness tester. As we all know, the base materials micro hardness was around 57.9 HV. In case of stir zone, in the composite specimen, the micro hardness was around 75 HV. So this demonstrates the ability of the composite to resist plastic deformation, and also the presence of uniformly distributed nanophase silica particles within the matrix. So here we can see the typical M type of trend, this inverted U type of trend in case of hardness when we traverse from base material, stir zone, and towards the base material again. And coming towards the immersion corrosion test, we have utilized the same Delbecque's phosphate buffered solution. We have done the immersion corrosion test in thermostatic water bath, mimicking the human physiological environment. And the corrosion products were cleaned using chromic acid, which is prepared by 100 milligram of chromic acid in 1000 ml of distilled water. So after doing the experiments, we have observed that the corrosion rate of AZ91D as well as the composite is so much, what to say, the corrosion rate of this AZ91D composite is so much better than the base material. So the corrosion rate comparison is just shown over here. So we can see that the corrosion rate of the base material is around 4.73 mm per year, and that of the composite, it is around 0.65 mm per year. And after 7 days of immersion, this base material had 1.05 mm per year, and this composite had 0.26 mm per year. So we can see that the corrosion rate have decreased a lot with respect to the base material, and it is in line with the requirement of us. That is, the corrosion rate should be very much below 0.5 mm per year, which is the recommended corrosion rate for biodegradable implants. So that is also evident. However, the initial corrosion rate of this composite is also still higher. So it is 0.15 magnitude higher than the required one. So we have been working on fabricating composite with improvised corrosion resistance properties. So we have fabricated HAP that had around 0.3 to 0.4 mm per year. So we have demonstrated it. But even if we are working right now with magnesium silver alloys, that will have better corrosion resistance too. And coming towards this crack features in base material as well as composite, we can see that there is fewer cracks after 3 days of immersion in case of composite, whereas we can observe a lot of cracks with branched structure in this base material. And corrosion product formation is so much lesser in case of the base material, whereas it is somewhat higher in the composite. And the distribution of corrosion products is scattered in case of the base material, whereas it is completely covered in case of the composite. So that could be one of the possible reasons why we have got an improvised corrosion resistance in the fabricated surface composite. So here is the surface morphology images that is taken using scanning electron microscopy. So these are the corresponding images of base material as well as the composite after 3 days and 7 days of 3 days and 7 days of immersion respectively. So here we can see that there is little formation of corrosion products after 3 days, where we can see a lot of corrosion products in case of a composite after 3 days of immersion. So added to that, the cracks are completely branched structure in case of this base material, whereas in case of composite, it is somewhat narrow as well as it is not branched at all. So these things indicate that the corrosion resistance of composite is somewhat better than that of the base material. Also, we have done this EDS, XRD, and phase analysis. So I'm not going to elaborate this again, and I'll elaborate the corrosion mechanism in detail for this particular case. So generally, the surface of magnesium has magnesium oxide film. So this magnesium oxide is a cubical structure, a cubical crystal lattice. And when it is immersed in any sort of a liquid medium, it will be transformed into magnesium hydroxide, which is having a hexagonal crystal lattice. So this hydration of magnesium and dissolution of magnesium oxide and deposition of magnesium hydroxide increases the volume of the surface, the topmost surface, and that leads to formation of surface cracks, and that indicates the porous nature of magnesium hydroxide. So typically these magnesium hydroxides are defect sites which are ideally suited for corrosion of magnesium. Why? Because they are completely porous in structure and they have a lot of cracks on the surface too. So added to that, as we have discussed already, there will be evolution of hydrogen gas in the course of immersion test. So when hydrogen gas evolves, that will stir out this magnesium hydroxide deposited over the specimen surface, and that also contributes to staking of corrosion inhibition. So when there is some phenomenon going on like this, then there will be an increased chloride ion concentration within the SPF solution, and these chloride ions are preferentially absorbed over the magnesium surface. So what happens is this small radius chloride ion will penetrate into the corrosion layer, and that will convert magnesium hydroxide into magnesium chloride. And the high solubility of magnesium chloride in the electrolyte or the human body simulated human body solution creates many exposed sites, and that in turn promotes further corrosion of magnesium. So This creates accessibility for magnesium ions to phosphate ions as well as calcium ions, and that in turn results in the formation of calcium hydroxyapatite or calcium magnesium phosphate layer. And these phosphate layers are completely compact, and that is why we end up with retarded dissolution rate. So that results in decreased corrosion rate in case of composites, and that is evident from the immersion corrosion test results too. And this particular layer reduce the permeability of calcium ions and phosphate ions into the matrix. So that is why we have observed many peaks and many many counts in case of calcium, phosphorus, and oxygen in EDS analysis, and that is why we have observed more corrosion products on the surface of composite than that of the base material. So that has to be understood. So with this, we'll just go on to the electrochemical aspects of this composite that is developed. So as we all know, electrochemical cell is made by electrodes. So we have three electrode system, that is anode, cathode, as well as a counter electrode in case of electrochemical corrosion analysis, whereas in case of electrochemical cell we'll have only two electrodes, that is anode as well as cathode. So anode is the electrode where oxidation reaction takes place, and cathode is the one where reduction reaction takes place. So the liberation of electrons determines the activity of the materials, and based on this standard redox potential against standard hydrogen electrode, we have formulated the galvanic series. So magnesium occupies the first and foremost position, so that has a very high activity. So that that is already discussed in our previous slides. So to analyze the electrochemical aspects of materials, generally we go ahead with polarization method. So here we have to deliberately change the electrode potential from equilibrium to a desired value. Then we forcibly make the electrode to behave as cathode by polarizing the specimen towards a more negative potential. Then we forcibly make the electrode to behave as anode by polarizing the specimen towards more positive potential using a potentiostat in electrochemical oxidation. So by doing this, we check if there is a limiting current tendency exists for the material, and then we investigate the corrosion mechanism. So added to that, we analyze if there is if the corrosion mechanism is dominated by activation, that is charge transfer kinetics, or the corrosion mechanism is dominated by concentration kinetics, that is mass transfer kinetics. So coming towards our analysis, we have taken the simulated body fluid, 37 degrees Celsius, everything is common, but the thing is we have used electrochemical oxidation and particularly potentiodynamic polarization method for analyzing the electrochemical aspects of the fabricated material. So here we have taken working electrode. Here the working electrode's potential is controlled and the current is measured. So this is going to be our specimen. The reference electrode measures the working electrode potential, and that will be constant with respect to its potential as long as no current flows through it. So typically people use standard calomel electrode or silver chloride electrode for reference electrode. So in our case, we have used standard calomel electrode for reference. And coming towards the counter electrode, we have utilized platinum for our case. So coming towards the concepts, I'm just going towards over here. So initially we have established open circuit potential for a period of 700 seconds. Once the potential is stabilized, then we have done this potentiodynamic polarization between that given range of minus 2.5 volt to plus 2.5 volt, and the specimens were polarized at a scan rate of 5 millivolt per second. And we have seen that the Tafel region's corrosion rate in case of base material is around 4.49 mm per year, which is in line with our immersion corrosion test results. And typically in case of the surface composite that is fabricated, we have observed that the corrosion rate is very much similar to the immersion corrosion test results. So that is obvious. However, we have seen a difference between the this potentiodynamic polarization plot with respect to base material as well as the composite. So the base material one is shown in red and the composite one is shown in blue colored one. So we have observed analogous cathodic kinetics in case of nanophase reinforced composite material as well as the base material. Why? Because the nanophase silica particles have significantly lesser effect with respect to cathodic kinetics. Whereas we have observed unique anodic dissolution characteristics. So that is why, because of the influence of friction stir processing as well as nanophase particles within the matrix. So here we can see the base material, the anodic curve is something like this. It just goes exponentially higher. Whereas in case of surface composite, we can see there is a step and there is again a step and then it stabilizes. So there is a significant difference between this base material as well as the composite developed. So we have to analyze why is it. Added to that, we have analyzed that the corrosion potential of this AZ91D, sorry, I mean, after corrosion potential, the current of this AZ91D increases exponentially, and that shows the high anodic dissolution of magnesium. Whereas in case of the composite that we have fabricated, after corrosion potential, there is a pseudo passivation tendency in the composite. So that is because of the presence of partially protective corrosion product film. So that is formed between minus 1.30 volt and minus 1.145 volt. And after minus 1.145 volt, there is breakdown of corrosion product film, and that resulted in an increased anodic dissolution of magnesium. And that is why we are seeing a typical increase in anodic current too. However, when we see the corrosion potential of base material as well as the composite, we observe that corrosion potential of base material is 0.018 noble than that of the composite. And the corrosion current of this composite is 3.56 times lesser than that of the base material. So that is a completely contradicting response that we have received in case of this electrochemical corrosion analysis. So we thought of analyzing this in detail using atomic force microscopy so that we can analyze how the surface work electron function is going to be distributed over the surface of base material as well as this composite that we have developed. So this could be explained based on the intrinsic electrochemical behavior that is influenced by the electron work function. So this electron work function is the minimum energy that is required to extract an electron or an electron pair from the subsurface without loss of any kinetic energy. So this low electron work function means that there is high tendency for the electrons to take part in any sort of chemical reaction. And obviously, if it is high EWF or high electron work function, it means that the electron reactions are going to be very much sparse. So in case of magnesium, the electron work function is around 3.6 electron volt, and that of silicon, it is 4.8 electron volt. So because of the dispersion of nanophase silica that has a very high electron work function over the surface of AZ91D in case of surface composite, that resulted in retarded dissolution rate. Why? Because the availability of magnesium for reaction to take place is very much limited. So that is why the corrosion rate is still lesser, even if the corrosion potential is somewhat anodic in case of composite. So that could be understood based on this. So for that, we have done this AFM map. So the AFM map is just shown over here for our reference. So here we can see the surface potential of the composite is way higher wherever there is nanophase silica particles embedded on the composite material. So this has been confirmed through this analysis too. So added to that, after this electrochemical workstation, electrochemical analysis, we have done surface morphology analysis too. So after this potentiodynamic polarization, there is distinct formation of corrosion product as well as features in case of corroded sites. So that also could have contributed to a reduced corrosion rate in case of this composite specimen with respect to the base material. So here are the major outcomes of this composite that we have developed. So the surface composite was successfully fabricated by dispersing nanophase silica, and through metallurgical analysis, we have confirmed the presence of refined grains, fragmented beta phase, and homogeneously dispersed nanophase particles. And corrosion test results indicate the formation of calcium hydroxyapatite and calcium magnesium phosphate layer that reduces the corrosion rate of the fabricated composite. And cumulatively, we can say that AZ920 silica reinforcing is going to be a good material or an effective material for bioimplant application. However, the corrosion rate has to be still reduced, as I have said earlier, why? Because we have 0.63 mm per year, that should be reduced to 0.5 mm per year. So that work has been carried out in line with this research after this by using nanophase as well as micron phase of hydroxyapatite. In that, we have achieved biocompatible as well as corrosion rate, which is very much less than 0.5 mm per year. Okay, so if time permits, I could go ahead with improvising creep resistance of rare earth-based magnesium alloys, or else we could have a short discussion right now.
Sir, we have around 5 minutes for time left for the session. If you could conclude with that, then we would go with. Otherwise, we would go for the discussion.
Yeah, sir. So that's fine. So I think this is the concluding slide. So we could go ahead for discussion directly. Thank you.
Okay.
Yeah.
Dear participants, if you have any questions, please unmute yourself and speak. Otherwise, if you have any kind of problem in network issues, then you can write it on chat box. Okay. Sir, I do have a question from Dr. Pankaj Kumar Singh. You can direct it towards the speaker.
Okay, myself, Dr. Pankaj Kumar Singh from IIT BHU. Your
Yes, sir. Please go ahead,
presentation,
sir.
your presentation was nice.
Yes.
My
Thank you,
question
sir.
is you have used AZ91D,
Yes, sir.
the alloy. What I know that A and Z, that is the aluminum, and Z, that is the zinc, and there is the magnesium also. Okay,
Yes, sir.
what is this D, AZ91D? What this D means?
Actually, that D indicates the purity level of that alloy specifically. So we have grades ranging from D, E, F. So we have used specifically this AZ91D grade explicitly in our research. So even higher purity grades are available in market right now, sir.
Okay. It is having some value also.
I think it is not the values. I hope it is the purity level. Correspondingly, we have those letter indications, alphabetical letter indications.
D indicating how much purity?
So I don't have that exact numerical values with me right now, sir. Maybe I could share it later.
Okay, thank you.
Yes. Yeah. Thank you, sir.
Okay, participants, any more questions? Either you can unmute yourself and talk to speaker directly, or you can write down in the chat box where I will direct it to the speaker.
Possibly, I could be available using these mail IDs that is given in this slide. Participants can directly either mail their questions or they are free to ask right now. I think we have a question in the chat box.
Yes, sir. Sir, Murli TG
Okay.
is asking what is the main limitation of using pure magnesia for biomedical implants?
Yeah, that's a good question. As I have discussed earlier, magnesium has very high corrosion rate with respect to simulated body fluids. Its corrosion rate will be as high as 4 to 8 mm per year when we use pure magnesium. So that is why people started to explore the utility of magnesium alloys, and subsequently, right now we are in magnesium alloy composites so that we can have decreased corrosion rate within the human body environment.
I hope that answered your query, Mr. Murli TG. Dear participants, we do have time for sessions. So please, if you have any questions, as written earlier, you can write down in chat box or even directly direct it towards the speaker. Dr. Vignesh, I do have a question from my side.
Yes.
As we have seen that in ceramic and in glass corrosion, there forms an protective layer
Yes.
during its corrosion.
Yes.
Is that part is also being looked after for these kind of alloys? Because as you saw in the slides, in the graph you mentioned, there was an particular stage at which you want the corrosion to be slowed down so that the bone can heal properly.
Yes. Yes.
Was this prospect also viewed in this study?
Yes, that's a good question. So we have not looked upon exact, what to say, in vitro analysis of specimens. We have done only in vivo analysis. However, the formation of this phases, particularly this hydroxyapatite, this calcium magnesium phosphate, is giving us promising results. Why? Because they are mimicking the bone material, innate bone material. So which means that if they are formed, that will help in healing of bones in a quicker period of time. Why? Because more cells will be attracted towards that hydroxyapatite crystals that is formed over the implant. So that will help in bone healing in a very quick way.
Okay.
Yeah.
Thank you, sir. Thank you.
Thank you.
So we do have one more question over here from Dr. Jaivalu Sundaram. He's asking that magnesium oxide plus tricalcium phosphate, is it possible for biomedical application? Through and one more question is, can we prepare these alloys through casting?
Yeah, while we prepare magnesium alloys to casting, we have to take care of many things. Okay, so first is the oxidation tendency as well as the reactivity of magnesium with the external environment. So we have to be very cautious by maintaining environments such as argon or SF6 predominantly used for fabricating magnesium alloy composites. That could be done. I'm not sure about this magnesium oxide plus tricalcium phosphate, but magnesium alloy based thing can be done through normal casting procedures too. But we'll end up with unnecessary porosities and sort of impurity inclusion possibly in casting wood. That is why we avoid, we just go ahead with solid state processing in case of magnesium while we fabricate composites. If there is an opportunity, we can go ahead.
Okay, so we do have one more question from Professor Dr. Rajat Hegde, sir. Sir, you can go ahead, sir, now.
Thank you, Deepankar. Thank you very much.
Yes.
Dr. Vignesh, it
Yes,
was
sir.
an excellent talk that you gave today.
Thank you, sir.
You shared a lot of information on magnesium-based alloys. I have one, it's not a question, in fact, I just want to know how it behaves. For example, if there is a transition of magnesium from crystalline to amorphous state, that is a metallic glass.
Okay, sir.
How does it behave as a biomedical implant when there is a transition from crystalline to bulk metallic state?
Yes, people have started to explore the utility of this metallic glasses actually for biodegradable implants as well as for bio implants. However, I have not worked on that explicitly, sir. So I'm afraid I could not answer this question explicitly right now.
Thank you, Dr.
Yeah.
Vignesh.
Thank
And
you.
thank you for accepting our invitation to deliver the talk. It was an excellent session today.
Thank you,
Thank you,
sir.
Deepankar. Thank you.
Thank you, sir. Thank you. Participants, any more questions? You can either unmute yourself or write in the chat box. I will direct it towards the speaker.
One last question, sir.
Please go ahead, sir. Please go ahead.
Actually, there is a formula that AZ group, like AZ31, AZ96, and 91, and other things are coming.
Yes, sir.
Whatever I want to just confirm from you whether I am correct or not.
Yes, sir.
That the AZ91D, it is having, I think, A, that is aluminium, that is 90%,
No,
9%,
no,
sorry.
9%. Yes, sir.
And 1% that is the jet, zinc,
Zinc. Yes.
and rest that is the 90% that is the magnesium, I think.
Yes, 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 sir.
Whether I am correct?
Yes, yes, that is how designation comes for magnesium. So A stands for aluminum, stands for zinc, and subsequent letters stands for the approximate composition of those elements in this
Approximate
manner.
composition. It means it is not exact.
No, it is not exact. It is not exact. That should be in that typical range. So that is what it means.
Sir,
So in
I
our case,
want to know, sir, how I can know that exact amount? Is there any
so
formula to generate?
okay, so we have ASM handbook, sir. So in that ASM handbook, they'll be giving us the exact composition or the compositional limits for those particular alloys. So that could be seen through ASM handbooks, or we have this matweb.com. So they have given a good database for materials. We can go there, we can just check what is the compositional limits for any sort of alloys in that web site too.
Do you having some chart regarding that?
We don't have any, we have this table format, sir, actually. They'll be giving for each and every alloy series in that case.
Okay.
Okay. Maybe I
Where
can
it is
share
available, sir?
the website details as well as the ASM handbook where you can see those details. Maybe as a personal mail, if you could drop me a mail, sir. Yeah.
Okay. There is any link from where I can get that list?
Yes, yes. We have an open source link also. That is what I said. I could share it with you.
Can you share that, sir, in the
Sure,
chat box?
sure, sure, sir. I could share. Yeah,
Okay. Thank you, sir.
yeah. Thank you.
Dr. Vignesh, we do have one more question from
Yes,
Murli TG.
yes,
He is
sir.
asking whether due to magnesium deficiency, there would be a loss of potassium in muscle cell. Is this statement true, or can it if, influence in any type, any way of how exactly it can go into magnesium bio implants?
Okay.
I think it
So
was
I think
on his view of asking, so I
yes,
just
yes.
modified it.
So possibly this question could be for any sort of medical doctors over here. I'm not so expert in this field, so I'm afraid I could not answer this question too. Why? Because I'm not well aware how potassium is going to react with magnesium deficiency with respect to human body. If it is respect to metallic materials, I could try to answer, but this question, still I don't have an answer right now.
Okay.
Yeah.
Uh, Participants, again, if you have any questions, please go ahead. And or if you have any kind of network issues, a chat box is always present. Okay, if there are no more questions, then we would wind up this session. I again sincerely thank you, because this was a wonderful session and wonderful educative session about how exactly a magnesium implant, or how corrosion analysis has to be studied. As a student of ceramic corrosion, I was deeply and intuitively reformed about how exactly we can go into analysis of corrosion as well. So I can share my feelings with all the participants as well. It's a very good educative session. I thank you from the whole FDP team in JNNC Mechanical Engineering Department. So thank you all, and over to you, sir.
Yeah, thank you, sir. I thank you for giving me an opportunity to discuss what my research work has been carried out in the past 3 to 4 years. Thank you.
Okay, participants, we will go for a short break, and we will join here again at 11:45 for the session by Dr. Shashibhushan Arya. So please, we will be on time at 11:45. Take care until then. Okay, so we'll join by 11:45.
Yeah, thank you, sir.